Hello.
Hello, Dr. Sun.
Hey, Dr. Zhen. Thanks so much for giving the talk to us.
Yeah, thanks. Thanks for the invitation.
We'll just wait a few minutes for everybody joining. Honestly, we don't have a big class here, but everybody's have some wireless background, so I think it will be very helpful and benefit for them to have your talk
Sure,
here.
sure, no problem.
All right, I also have the meeting recorded. I can send you the recorded link after the talk.
Okay, sure. Thanks. Yeah, I
Yeah,
will also share the recording with some of my students. Maybe
great.
they're also interested.
Great. That'll be great. Okay, I think it's 10 o'clock now. I think we can get started. So first of all, let me give a brief introduction of our guest speaker, Dr. Yong Zhen from Southeast University. So first of all, for those who are not from China, Southeast University is I can say the top university in China for in the area of wireless communication. And we are very excited to have Dr. Yong Zhen, who is an IEEE fellow, and right now is a young chief professor of Southeast University. And he's also affiliated with the Purple Mountain Laboratory. And just very briefly for his achievement, he's the top 2% scientist in the world for a very long time, for 4 years, 4 consecutive years. And he's a recipient of a lot of Best Paper awards and a lot of other international awards, including the Hertz Awards, and that's a big one. Marconi Awards. I mean, all of those awards are big ones in the communication world. Today, Dr. Zhen will talk about one of his very recent research about the Delay-Doppler Alignment Modulation. I talked just a little bit about this modulation during the class, but I think Dr. Zheng is the leading person in the field. So I think he will go through that DDAM modulation with us today. So all right, I'll handle the talk to Dr. Zheng, and let me see. Okay, you can share your screen too.
Sure. Thank you. Thank you so much for the kind introduction. So let me share the screen. So can you see my screen now?
Yes, I can see.
Okay. Yeah, great. Okay, so first of all, I would like to thank Dr. Shen for the kind invitation and the introduction. So good morning, everybody. So today I would like to take this opportunity to present one of our recent work called the Delay-Doppler Alignment Modulation, or DDAM. So I believe that this will give us a new opportunity for the waveform design for 6G or even beyond 6G. So I will first briefly introduce the so-called ISI mitigation techniques from 2G to 5G. And then I will try to motivate why we need to propose the so-called Delay-Doppler Alignment Modulation. So before that, I will also introduce the special case called the Delay Alignment Modulation, or DAM, from the single carrier perspective and also from the multi-carrier. So how can we integrate DAM with OFDM? And then I will also introduce what if we only have a hybrid beamforming. So can we also apply delay alignment modulation? Then I will also introduce for multi-user scenario, how can we apply DAM for both ISI and the inter-user interference mitigation. Then I will introduce the more general case called the Delay-Doppler Alignment Modulation, or DDAM, followed by some very preliminary experimental results. And I will also introduce briefly how DAM can be applied in ISAC, or integrated sensing and communication. So we know that from 2G to 5G, so one of the biggest issue for wireless communication is how we mitigate the inter-symbol interference, or ISI. So for 2G, when the data rate is not very high, we may use the channel equalization. So we may apply equalization in the time domain or frequency domain. We apply equalization at the transmitter or receiver. So we may have the pre-equalization or post-equalization. Then in 3G, we have the spread spectrum and the receiver, like in CDMA systems. And in 4G and 5G, we have the very famous and very successful OFDM for ISI mitigation. Then what is after 5G? Do we have new opportunities or new motivation to develop new techniques for ISI mitigation? So to answer this question, we need to understand that different ISI mitigation techniques actually have their own pros and cons. For example, for channel equalization, we have the high signal processing complexity. Similarly, for receiver, at the receiver side, we have the high receiver complexity. For OFDM, we have the well-known PAPR issue, peak to average power ratio issue, and it is also very sensitive to carrier frequency offset. And if we have the large delay, we have large Doppler spread, we may have the inter-carrier interference. So recently, there is another technique called the OTFS, or orthogonal time frequency space, but it also has a high signal processing latency issue, and the receiver complexity is also quite significant. So actually, if we want to discuss whether we have new opportunity or new motivation to study new waveform design, let's take a look at some fundamentals for OFDM. So we try to ask the question, is it possible for us to achieve extremely low PAPR and with very few subcarriers, and also with very low CP overhead? So in this case, let's say we have a CP duration. We know that for OFDM, we have CP duration and we have the symbol duration. So if we we take the ratio between the symbol duration versus the symbol duration plus the CP duration, we actually have a very coarse approximation of the spectrum efficiency. So we really want the CP duration to be much smaller than the symbol duration, so that the CP overhead is negligible. So let's assume that we have certain threshold, ZTH, we need to satisfy. We want this ratio to be greater than certain threshold, for example, 0.8, 0.9, or even 0.99. So in this case, we want our CP duration to be much smaller than our symbol duration. But we have another constraint, which is that PAPR, peak to average power ratio. For OFDM, PAPR will increase with the number of subcarriers. So let's say if we want our PAPR to be smaller than certain threshold, basically we cannot use too many subcarriers. For example, we cannot use like 1024 or 512 subcarriers. That will cause too much PAPR. So although we have some techniques to reduce PAPR, this relationship still exists. So let's assume that we have certain threshold for this number of subcarriers and also this ratio. Actually, in order to achieve these two parameters, we have some feasible region for our channel delay and Doppler spreads. So with some simple mathematics, we found that in order to satisfy these two parameters, our delay spread, tau d, cannot be too large. We have a certain constraint, depends on the number of subcarriers and also depends on this spectrum efficiency, this ratio. And the Doppler spread cannot be too large because we have this constraint. Basically, this will give us the subcarrier spacing. It cannot be too large. So actually, in this paper, this is our recently accepted paper in Communication magazine. We actually have the same title as our talk title today. So Rethinking Waveforms for 6G, Harnessing Delay-Doppler Alignment Modulation. So in this article, we derived this simple relationship by finding the relationship between the bandwidth, number of subcarriers, and the subcarrier space, and so on and so forth. So they are very simple relationships for OFDM, and we got the feasible region for the channel delay and the Doppler spreads. So if we plot this feasible region for delay and the Doppler spread, we actually have the x-axis, we have the delay spread. For the y-axis, we have the Doppler spread. So if we are given certain number, let's say ρth and kth, actually we have this kind of rectangular region. Within this region, it is feasible. Out of this region, it is infeasible to achieve these two parameters. So if we increase this ρth, we will move to an inner curve. And if we try to reduce the kth, the number of subcarriers, actually our affordable or feasible delay spread will be reduced. For example, if we want to increase the extreme, achieve the extreme case with ρth approach to 1, with a single carrier, so kth approach to 1, we have this case. So this basically requires us that the delay spread should be very small if we want to achieve the extremely low PAPR and extremely low CP overhead. But in practice, for our time frequency double selective feeding channel, we do not have this delay spread to approach to 0. So in this case, is it still possible to achieve the extremely low PAPR and extremely low CP overhead efficiently? So this actually motivates us to propose new techniques. This is only possible if we can use some techniques to actually reduce our delay and Doppler spread without sacrificing the time and frequency resources. And this can be achieved by the delay and Doppler alignment modulation. So first of all, what is delay alignment modulation, DAM? So DAM actually makes it more possible or more feasible today because we have new developing trends for 6G. For example, as compared to 5G, we have larger antennas. So for example, we may shift from massive MIMO to XL MIMO. So in this case, we have very high spatial resolution, super spatial resolution in the antenna domain. And another trend is that we move to higher frequency bands like millimeter wave and the terahertz bands. So in this higher frequency bands, we have the so-called multi-path sparsity property. We do not have too many multi-path as in sub-6G signals. So in this case, it is easier to distinguish the multi-path signals. And we have the integration of the localization, sensing, and the communication. So instead of just estimating the channel in the time frequency domain, we can also estimate the parameters like the delay, Doppler for each path, because these are exactly the sensing requirement or the sensing task for ISAC for integrated sensing and localization and communication. So these three trends will actually give us new opportunities for ISI mitigation. We call it delay alignment modulation. For DAM, we actually performs the joint spatial and delay processing based on the path-based delay compensation and also path-based beamforming. So before we give the mathematics for DAM, let's take a look at the channel in different domains. For example, let's assume we have 5 multipath for this channel. These multipaths have different delays and Dopplers. So in the delay and Doppler domain, we actually have the very sparse representation. For example, this path have a cluster in this delay and Doppler, and the other path, they are separated. So they are quite sparse in the delay and Doppler domains. But in the time frequency domain, we still have the frequency selective. So for example, at a different frequency, the channels are different, and they are also time selective because the channel is time variant. But if we further plot the channel in the delay, Doppler, and also the angular domain, we can further separate the signals or the multipath, not just in delay and Doppler domains, but also in the angular domain, because the different delays and Dopplers, they may correspond to different angles. So this actually gives us the opportunity to separate the different path in the angular domain, and then after that, we can decouple the multipath signal in the angular domain. They will become independent. They become almost orthogonal. In this case, we can simply shift. Let's say we just move the different multipath signal in the delay and the Doppler domain so that we can reduce the delay and Doppler spread. This is only possible if we can separate or decouple the signals, the multipath signals in the angular domain, so that we can independently shift the signals in the time and in the delay and Doppler domain without affecting each other. So this will reduce our delay and Doppler spread. So this is the intuition, the basic idea. So mathematically, let's consider a very simple case. We assume that the base station has a large antenna array. So the receiver, for simplicity, we assume at the moment we only have one single antenna. But in the multipath environment, we may have the direct line of sight path, and we have the different reflection and the scattering path. So we may use a different notation. Let's say we have L multipath, and each path have a delay NL. And for each path, we have a vector for this channel path because we have multiple antennas at the base station. So if we plot the channel in the delay axis, so we have the large delay spread. Although the multipath can have sparsity property, the delay spread can be large because the first delay and the last delay can be very large. So in this case, actually, we can use the so-called delay alignment modulation. The basic idea is that we will purposely introduce some delay compensation at the transmitter side. So let's say Sn is our transmitter symbols. And we split these symbols into different branches. For each branch, we introduce a unique delay, kappa L. So this kappa L will be introduced so that it can compensate the corresponding delay of the channel. So we can say that, let's say the L's delay we introduced will be equal to some maximum delay we want to align minus the channel delay. So in this case, our channel delay NL plus our introduced delay, it will equal to a common value Nmax for all the L paths. And in this case, we still need additional performance, additional processing called path-based beamforming because we want to introduce different beamforming vector for each delayed signal. So with this, we perform a linear convolution of our transmitted signal Xn and our channel impulse response. We will get the received signal Yn. So we can expect that in this case, we have more delays or more channel passes because we have the multipath delay at the channel, and also we purposely introduce the delay at the transmitter. But remember that we have an additional design parameter, which is our spatial beamforming vector. So if we group the delay of, or if we group the path that corresponding to the common delay Nmax, we find that we have the signal contributed by all the L multipath signals. And this L multipath signals will be all aligned at the one single delay Nmax. And all the remaining terms, they will contribute ISI intersymbol interference. But we can design our beamforming vectors to make this coefficient to be 0. So in this case, if we can design our beamforming vectors so that this condition is satisfied, then essentially we will remove this intersymbol interference, and our received signal at the receiver without performing any additional processing will be just one single tap or one single delay. And this delay will be contributed by all the signal, all the multipath channels. So there will be no power loss, and all the signals will arrive at the receiver simultaneously and constructively. Okay, so in this case, we resolve the ISI intersymbol interference issue by just performing this very simple delay and beamforming. Okay, then the question is it possible to design the beamforming vectors so that these ISI terms will be eliminated? So the answer, yes, it is possible, as long as the number of antennas at the base station is no smaller than the number of multi-paths L. So this will be possible almost surely. Okay, so this is the zero forcing condition. So in this case, we can plot the transceiver architecture for this delay alignment modulation. So we have the information bearing symbols to be transmitted, but we do not directly transmit these symbols. We introduce the delay, different delays, and then for each delay, we introduce the beamforming vector, and we sum them up, and we will transmit over the empty antennas. Okay? So the transmitter processing will be also quite simple. So just now we mentioned that we want to achieve the intersymbol interference-free transmission. We need to perform the zero forcing beamforming. But this does not have to be zero forcing beamforming, because if our transmitter antennas is large enough, for example, if the transmitter antennas is much greater than the number of multipaths, we actually can have this so-called asymptotically orthogonal property. It basically means that the different multipath signals, they will become asymptotically orthogonal. So in this case, without having to perform zero forcing beamforming, we can still achieve the ISI-free transmission by simply performing the path-based MRT beamforming. Actually, this is quite similar to the massive MIMO system to eliminate the inter-user interference. As long as our base station antenna is much greater than the number of users, we have the orthogonal or asymptotical orthogonal property between the different users. We have the similar result if the number of antennas is much greater than the number of paths. So we have the similar result. So there's no need to perform zero forcing. So if we try to optimize the beamforming vectors for DAM, we have different techniques. For example, if the number of base station antennas is greater or is no smaller than the number of paths, we can perform the zero forcing or ISI zero forcing beamforming. Okay, and we actually can get the closed form expression for this ISI zero forcing beamforming. And we may also perform the MRT beamforming, the path-based MRT beamforming. We may also find the closed form expression for path-based MMSE beamforming. Okay, so all this will give us the closed form expression. It is not that complex. So if we compare the the frame structure for DAM versus the OFDM, we find that for OFDM, we need to insert one CP or one cyclic prefix for each OFDM symbol. Okay, so in this case, this CP will degrade our spectrum efficiency because the CP does not transmit new information. So we need to multiply some coefficient, some weighting factor to take into account the overhead due to the CP. But for DAM, we actually only need to insert one guard interval at the beginning of each channel coherence time. So in this case, we can actually significantly reduce the guard interval overhead. Okay, so this will also be verified in our simulation results later on. So just now we introduced the principle of the delay alignment modulation. We assume that the different delays can be aligned to be one single delay and max. Okay, this is called the perfect DAM. But in practice, we may not want to do this perfect DAM because it is a very strict requirement. We may relax the requirement. Let's say instead of trying to align all the channel passes into one single delay, we only want to reduce the channel delay spread. For example, without performing the alignment, this is our delay spread. This is the first delay. This is the last one. So we have the large delay spread. But after delay alignment modulation, we want our delay spread to be reduced. Let's say reduced to this value, and we achieved some partially alignment. So in this case, we have much relaxed requirement for delay alignment modulation. And then how about this residual delay spread or residual ISI intersymbol interference? Because this delay spread will cause intersymbol interference. But of course, we can use our other methods like multi-carrier transmission or channel equalization to address this issue. But in this case, we have a much smaller delay spread. We have much fewer effective channel or multipath, and this will make our OFDM design and also the equalization design has larger degree of freedom. For example, in this case, we may integrate our DAM, delay alignment processing, with our OFDM transmission. Okay, so in this case, the DAM will be performed in the time domain. So based on the path-based beamforming and the delay compensation. And the OFDM, we just perform the traditional OFDM, but in this case, the OFDM transmitter will see an equivalent channel after the delay alignment modulation, which has much smaller delay spread. So in this case, we can have more flexibility to choose the number of subcarriers, also to choose the CP overhead. So we can reduce the number of subcarriers to reduce the PAPR, as we mentioned just now. So this is also one of the motivation to use delay alignment modulation. We may also reduce the CP overhead, okay, without sacrificing, without reducing the spectrum efficiency, because we have a smaller delay spread. We can use a smaller CP duration. Okay, so this will actually give us a unified framework for ISI-free single and multi-carrier communication. So in the extreme case, we can reduce the number of subcarriers to be 1. This will reduce to the single carrier transmission, and we still do not have, we do not suffer from the intersymbol interference issue because we can perfectly align the delays. Okay, so and another new opportunity that now we have the beamforming in the frequency domain as in OFDM, and we also have the beamforming in the time domain for DAM. So we have a joint time and frequency domain beamforming. This will give us the more flexibility for single or multi-carrier communication. So in this paper, we have given the more detailed mathematical derivations. So let's take a look at some simulation results. Here we compare the conventional OFDM with different number of subcarriers and DAM after delay alignment modulation. So we found that for OFDM, depends on the number of subcarriers, the spectrum efficiency can be very poor, because if we use a smaller subcarriers, we have a larger overhead, okay, larger CP overhead. But this issue will be resolved by the DAM OFDM, because in this case, the delay spread is reduced, so we can use smaller, or we can use smaller subcarriers without sacrificing the spectrum efficiency. Let's say even for this only 64 subcarriers, you can still achieve a very large spectrum efficiency. Okay, and not just for the improvement for spectrum efficiency, for DAM OFDM, we can also reduce the PAPR, because after reducing the delay spread, we can reduce the number of subcarriers. In this case, we can achieve much lower PAPR and still achieve better spectrum efficiency. Okay, so this is a quite appealing or quite attractive benefits for DAM and the DAM combined with OFDM. So what if we only have so-called hybrid beamforming? So for hybrid beamforming, the basic scenario is that we only have a very few RF chains. So the number of RF chains is much smaller than the number of antennas. So in this case, we cannot perform the fully digital beamforming as we discussed just now. In this case, is it still possible to achieve delay alignment modulation? So this is still possible because we have the similar architecture. So this is SN, and we introduce the different delays. And at that, we will introduce the fully digital beamforming first. And then after RF trim, we will perform the additional analog beamforming or analog pre-coding. So the transmitted signal will be quite similar to the fully digital beamforming based DAM. The only difference is that we need to split the beamforming into the baseband or digital domain and the RF domain. So with this, we can still have the similar received signal with this part replaced by two portions, two parts. So this is the baseband beamforming. This is the RF band beamforming. So all the remaining parts will be quite similar to the fully digital beamforming case. So in this case, how can we design the baseband beamforming and the RF band beamforming? So we can actually first perform the fully digital beamforming design to find the optimal fully digital beamforming, and then we only need to perform an additional optimization so that these two parts, they multiply together. We try to get as close as possible to the optimal fully digital beamforming. So in this case, we can find the optimal or close to optimal design for this hybrid beamforming based delay alignment modulation. So without giving the details, we give the performance comparison. Let's say we plot the spectrum efficiency versus the number of antennas. We consider the fully digital beamforming and the hybrid beamforming as well as the OFDM. We find that with this hybrid beamforming, as long as the number of RF chains is not too few, we can achieve comparable performance as the fully digital DAM system. And it can still outperform the DAM system because we can reduce the guard interval overhead. Okay, so similar for the PAPR performance, we can reduce the peak to average power ratio by using DAM. And then how about the multi-user scenario? Just now we only consider the single user. For multi-user, so different users, they have the own channel impulse response, the different delays, and for each delay, it has the different channel vectors. So in this case, the transmitted signal by the base station antennas will be a summation of all the users. For each user, we need to split the signal into different path or different delay compensation. So the transmitted signal will be given by this form. And the received signal, we will have the inter-symbol interference for each user K. We still have the inter-user interference. And we also have the inter-symbol interference, sorry. Here is the inter-user interference. But similar to what we discussed just now, this inter-symbol interference can be removed if we design the beamforming vector like this to achieve this zero forcing condition. And we can also design the beamforming vector to remove the inter-user interference. Okay, in this case, we just have the ISI and the IUI-free AWGN channel. So the receiver processing will be very simple. Without doing anything, we just see a equivalent channel, just like an AWGN channel. And this channel will be contributed by all the paths of this user. So there will be no power loss. Okay. So this is also feasible if the base station antennas is large enough. And if the base station antennas is much greater than the total number of multipath, we do not need to perform the zero forcing beamforming. We still can perform the path-based MRT beamforming because all the multipath signals whether it is from the same user or from a different user, it will become asymptotically orthogonal, and this will simplify our transmitter design. Okay, so this will give us a very simple result at the receiver. So we also compared the multi-user delay alignment modulation with two benchmark schemes. So the first benchmark is that we just perform the so-called single pass or the strongest pass-based beamforming. So for each user, we determine which is my strongest path, and I will just design our beamforming vector toward this strongest path. So in this case, we do not need to do the delay alignment, and we do not need to do the multi-carrier transmission. And we can also address the ISI issue. And another benchmark is, of course, OFDM. So we found that DAM, so in this case, this is the performance for DAM versus the number of multi-pass, will outperform the two benchmark schemes. So for the comparison with OFDM, we know that the performance gain is due to the reduction of the CPU overhead. Also, as compared with the strongest pass-based beamforming, the performance gain is due to that DAM will utilize all the multi-pass signal, but the strongest pass will only utilize one single multi-pass, right? So we can expect that if the number of multi-pass is larger, this strongest pass beamforming will get the performance will be very poor. Okay, so this is the performance gain as compared to the strongest pass beamforming, and it also demonstrates why we need to do delay alignment modulation. Okay, so similarly for the PAPR, even for the multi-user case, we can have the performance gain as compared to OFDM for PAPR. But as compared with the strongest pass beamforming, the PAPR of DAM is larger because for the strongest pass beamforming, it only uses one pass, so the signal variations will be smaller. So this is the basic idea for delay alignment modulation, or DAM. So next, we want to extend the technique to DDAM, or Delay-Doppler Alignment Modulation. So for delay alignment modulation, we assume that the channel is stationary, is constant. But in practice, we have time-varying channel. So for each multipath, we not just have the delay, we also have the Doppler. So for each multipath, let's say we have the Doppler nu L and the delay ML. So in this case, our channel impulse response will have two parameters, the time index N and also the delay index M. So in this case, let's say we have L multipass, then the channel can be represented by the delay ML and also the Doppler frequency nu L. And we have the channel matrix. In this case, we consider multiple antennas at the base station and the user. So for each multipath, we have a channel matrix instead of the channel vector. So this will give us the channel impulse response for the MIMO time invariant frequency selective channel, so doubly selective channel. So we can apply the similar idea as delay alignment modulation to not just compensate the delay, but also to compensate the Doppler. As long as we can estimate the Doppler of each path, we can also introduce this so-called Doppler compensation. We found that we just need to introduce the phase rotation with a rotation frequency similar to the same as the Doppler frequency as our path or as our channel. So in this case, after convolution with between this received transmitted signal and our channel, our Doppler will cancel and our delay will also be canceled. So our desired signal will not have any time variation. There will be no Doppler and it will only have one single delay. And the signal will be contributed by all the multipass signals. Okay, so there will be no power loss. How about the intersymbol interference? The intersymbol interference, it will be time variant because we cannot perfectly compensate the Doppler for the intersymbol interference term. But this does not really matter because we really want to design our transmit and receive beamforming vectors to remove this intersymbol interference. And this is feasible under some certain conditions. So in this paper, we derive when it is feasible to remove this intersymbol interference if we have multiple antennas at both the transmitter and the receiver. Okay, so if we plot the transmitter architecture for this DDAM, it is quite similar to DAM. We have the information bearing symbols. So in this case, we may transmit multiple data streams. So this can be a vector, not just a scalar. Then we have the delay precompensation, and then we introduce the phase rotation based on our channel phase shift. And this will compensate our Doppler. And after the beamforming matrix, we will transmit the signal over the multiple antennas. Okay, so at the receiver, we may also perform the similar performance. Okay, so in this case, we may also have the asymptotic result. If our antenna's MT is much larger, we do not need to perform the zero forcing beamforming. We can perform the simple MRT beamforming. We can achieve the similar time invariant, although the channel is time variant, because we have performed the Doppler compensation. Now, after the DDAM, the channel is no longer time variant, and we do not have the intersymbol interference. Okay, this will make the receiver design quite simple. So let's take a look at what really happens. What really happened after the DDAM. Okay, so this is our transmitters. This is the symbols we want to transmit. We can perform the conventional modulation of beamforming, whatever you want. And this is the DDAM processing, and this is our channel. And at the receiver side, we can perform whatever demodulation. Okay, so let's zoom in this part, DDAM and the channel. So the input to the DDAM is a time domain sequence, the time domain signals, DDAM. It can be after the frequency domain beamforming or after whatever, let's say OFDM transmit modulation, so on and so forth. We do not really care, but DN will be our time domain sequence. So for this time domain sequence, we introduce the delay and we introduce the Doppler compensation. So for each of, for this part, okay, for this part, we actually equivalent to view the channel after this beamforming vector. Although the channel has multipass like this, we have many different clusters of the multipass in the delay and Doppler domain. After this pass-based beamforming, we only actually we have only one pass, one cluster in the delay and Doppler domain. Here we have another cluster. Here we have another cluster. Okay, so we actually decouple the channels in the spatial domain with this beamforming matrix. And then we just perform the delay compensation and the Doppler compensation because this branch will only affect this pass, and this branch, the delay and Doppler compensation will only affect this path. So in this case, we can align the different path after the delay Doppler compensation. So essentially, we only have one single point here after DDAM. So this will achieve the alignment. So in the time frequency domain, we do not have any frequency selectivity like this, right? Over the different frequency, the channel is almost a constant. Okay, we also have a very large time channel coherence block. So the channel time variation will also be very small. Okay, so this will actually tell us what really happens after the DDAM for each step. Okay, so with this we can design our transmit and receive beamforming vectors, and we will not give the details. So we can also compare the DDAM with OFDM. So for OFDM, we can compare whether we consider the CP overhead with or without considering the CP overhead effect. We find that the DDAM can still achieve much better performance as compared to OFDM because we can save the CP overhead, and also for the strongest pass beamforming, as we mentioned just now, we can have much better performance as compared to strongest pass beamforming because we make use of all the channel passes. And if we can also compare DDAM with OTFS, okay, we found that DDAM still outperform OTFS because as compared to OTFS, we may also reduce the CP overhead. And at the different velocity, we compare the BER performance of OFDM as compared to DDAM. We found that at a high velocity, DDAM can have better performance in terms of the BER performance because it has much higher resilience to the ICI issue, intercarrier interference issue. And also the PAPR performance, we have the similar performance as compared to OFDM. Okay, so this is the basic idea for DDAM. Now let's introduce some very initial result for prototyping. We actually implement the DAM based on our system. So we use an USRP as a transmitter, another USRP as a receiver. We use the phase antenna array for the transmitter. So we consider a very simple scenario, two passes, only two channel paths, the direct path and a reflected path. So we estimate the path delays and the path gain of the two passes, and we perform the delay compensation. Okay, so this is the result for the delay measurement. We found that the delay difference is about 12 nanoseconds. And with this information, we can perform the delay alignment modulation. So this is a constellation without performing delay alignment modulation. And we found that it cannot really achieve any meaningful communication. But with delay alignment modulation, we can see the constellation points. Okay, so we also compare the case with the strongest pass, so or with one single pass. So this is very similar to the benchmark we mentioned just now. We only make use of one single path without considering the other paths. So this is the case if we only use one path, path one. This is the case if we only use the second path, path two. We found that as compared to our proposed DAM, so path one and path two, because of the only use one single path power, it has much worse performance as compared to our proposed DAM. So this actually shows the benefit to perform delay alignment modulation. So finally, let me briefly talk about the integration of DAM with ISAC, or integrated sensing and communication. So for ISAC, the basic scenario is like this. We have an ISAC transmitter. So we have a transmitter antenna array and a receiver antenna array. The transmitter will transmit one single waveform to the communication receiver and also to the target. The target will reflect the signal to the receiver antenna for the ISAC node to perform sensing task, for example, to estimate the velocity, to estimate the direction of this target. So with this, we can achieve the simultaneous communication and sensing by using one single waveform, by using one single device. So we can model the communication channel. Let's say it is a multipass channel. We have L multipass signals. And we have the sensing channel. Let's say we have the direct enough side channel with this sensing target with some delay tau and with some velocity or with some Doppler nu. So in this case, we may consider to use different waveforms to perform this ISAC. For example, we may use single carrier FDMA, we may use OFDM, we may use FMCW. So this is the sensing waveform or radar waveform. But these waveforms, they have different limitations, as we mentioned just now. Another possibility is that we make use of the DAM waveform, as we mentioned just now. So the DAM waveform, the benefit is that for communication, it can achieve ISI-free communication, and it can reduce the PAPR. This is quite useful for sensing because for sensing or for radar, PAPR, if we reduce the PAPR, it means that we can use higher transmit power. It will increase our sensing range. This will be very critical for radar sensing. And it is more robust to Doppler frequency shift. This basically means that we can sense the target with larger Doppler, and it is quite attractive for sensing. So this will make our DAM waveform quite appealing, quite attractive for ISAC. Okay, so in this case, we integrate ISAC with DAM, and we have one paper published in TWC. So in this case, we try to design our beamforming vector. We try to balance the communication performance. For example, we try to maximize the communication power received at the communication receiver. And we do not want intersymbol interference, as we mentioned just now. So this is a condition for ISI-free transmission or communication. And we have the total power constraint. And for sensing, we also want to have a constraint. We want the sensing target or sensing SNR to be largest in certain threshold. And we also want to impose some constraint for the so-called integrated side lobe ratio so that we have better sensing performance. So we can perform the optimization problem. After the optimization, we can find that we can achieve the desired communication and sensing performance. For example, these are the directions for our communication multipath signals. We found that we can form some beams toward these directions so that we can collect all the powers along these directions. And for the sensing directions, we also have a one beam so that we can achieve the simultaneous sensing and the communication without any intersymbol interference. And similarly, we can achieve the PAPR performance gain. Right? We can reduce the PAPR. And for sensing, we may also compare with the velocity estimation as compared with OFDM, because for single carrier DAM, we can achieve better performance for velocity estimation because we have a larger subcarrier spacing, right? So it is more robust to Doppler shift. So this actually basically gives us all the major content for this talk. So in this talk, I firstly try to motivate why we need to propose DAM or DDAM. And then we give some intuition for delay alignment modulation. And we consider the single carrier DAM and how DAM can be combined with OFDM. Basically, it will reduce the delay and Doppler spread. And then we will introduce the DDAM and some prototyping and experimental results. And the DAM can be also used for ISAC. But actually, we have many more future directions to work with. For example, how to further reduce the complexity for DDAM. For near-field DDAM is also one of the directions we are working on. And for some cluster-based channel models, we have more complex channel models, the performance analysis and the improvement for DDAM, and also non-ideal conditions, and also the multiple access for DDAM, and so on and so forth. Okay, so these are the major references. We have some papers published in TCOM, TWC, and COM magazine, and so on and so forth. Okay, so these are my major collaborators, some professors, and my students. Okay, so that is all for my talk. Thank you very much.
Right. Thanks so much. I think this is a very informative and it's a very good talk. So first of all, any question from the students? If you want to ask a question, you can unmute yourself and then just feel free to discuss. No, it's very quiet. Okay. Let me ask some questions and maybe the students can follow up. So I think when we talk about delay and Doppler, a common strategy or something we heard before is the OTFS. So what do you consider the major difference between the DDAM with the OTFS in terms of like some high-level differences?
Yeah, that's true. Yeah, so DDAM and OTFS, they have some similarities. For example, they try to exploit the sparsity in the delay and Doppler domain. And for DDAM, I think one major difference is that we not just exploit the delay and Doppler sparsity, we also try to make use of the spatial dimension to use multiple antennas to firstly distinguish or decouple the different multipath in the spatial domain. So in that case, as long as we can decouple the multipath in the spatial domain, they become independent in the delay and Doppler domain. So we just do the simple alignment. They will not affect each other. And then everything will become very simple. Right? But for OTFS, they do not really explore too much about the spatial domain. So when we try to combine OTFS with massive MIMO or XL MIMO, actually the complexity will be very high. It will be much more complex. It is not that straightforward to combine OTFS with massive MIMO or even XL MIMO. So maybe there are some initial works, but it is not as straightforward as DDAM. And another difference is that for OTFS, it is a kind of a frame-based processing. So as I mentioned here just now, so it has a limitation like we have the larger latency for the signal processing. So this may not be desirable. And also the complexity of the receiver is also quite significant. So actually we have some numerical or some analytical performance in terms of the complexity and the performance between DDAM and OTFS and OFDM. And we have some, of course, there are some different trade-offs. For DDAM, of course, we have our own limitation. For example, we want to estimate the channel delays and Dopplers. So this is basically a sensing problem. And we try to integrate this sensing and communication. This is also one very good point to consider ISAC and communication, sensing and communication, because now we really want to perform the sensing, and then the sensing task will just be like our channel estimation for DDAM. So they just need to perform one task, right? But another limitation is that we need to have large antennas. We need to distinguish our signals or multipaths in the spatial domain, but this is not a requirement for OTFS. So there are pros and cons for different techniques. Yeah.
Right. So the DDM is more like using a beamforming technique or similar to the beam technique by using like and then OTFS has more sophisticated signal processing. That's a very good point. So in terms of like the supporting the high velocity or high speed communications, what do you think the pros and cons with the OTFS?
Yeah, I think if we can estimate the delays and Dopplers, they both have similar performance. But for DDAM, for OTFS, it does not have to estimate the Doppler at the beginning, because we can just perform the transforms, so many transforms, ISS FFT transforms, without using the Doppler or delay information. But for DDAM, we need this information. But if we can estimate this information, I don't think there is much difference in terms of the supporting high velocity. Yeah, that is my understanding. Yeah.
Sure. That's very good. Any question from students? Final chance. We are approaching midnight. Anyone? Okay. I just wanted to have a follow-up. I sent you the some of the works that we have done. I think that would be a great framework for estimating the pass using some like computer vision techniques. You can directly estimate the pass as well as the delay. So it's just like looking at the environment, then you can know which the signal coming from which pass. That is so-called the multi-pass profile or special spectrum. I think that would be a very good combination with DDAM or even just DAM if we consider about the stationary scenarios.
Yeah, I think that is really a very good point. Yeah. Okay.
Great. Thanks so much. It's already midnight in China, and
Yeah.
thanks so
Yes.
much for
Yeah.
your talk today, and we really appreciate that. Okay, I'll
Thank
send
you.
you
Thank
the
you.
recorded link after it may take some to process, but I will send you the recorded link.
Sure.
Let's thank Dr. Zheng, and that will be it for today's talk. Thanks so much.
Okay. Thank you.
Thank you.
See you. Bye.
Bye.
Thank you.
Thank you.